We casually use the word smart to describe everything from watches to refrigerators. But in modern engineering, smart is an incredibly low bar. The lowest here is simply a smart device. If you program a coffee maker to brew at 6 a.m., that hardware has localized automation, but it is entirely isolated. It requires no network. The next tier introduces basic telemetries. These are connected devices, your Bluetooth speaker, your smartwatch, or a Wi-Fi-enabled security camera. They can be monitored or controlled remotely, but they still lack systemic intelligence. That brings us to the highest tier, true Internet of Things systems. This diagram illustrates the shift. IoT is a software-defined ecosystem, merging physical hardware, networking, and analytics, turning devices into mere endpoints. This architecture scales infinitely, upgrades dynamically, and adapts to future demands without replacing underlying hardware. To engineer these systems, developers must look past the consumer product and master the underlying structural stack. Every scalable IoT ecosystem, whether it runs a localized smart home or an entire smart city, functions on a strict, standardized three-layer hardware architecture. This diagram shows the three layers, starting at the bottom with the perception layer. This is the physical interface. It acts as the boundary where real-world conditions are captured and translated into raw digital data. Microcontroller units, or MCUs, provide the localized processing power needed to operate the hardware. These controllers drive the sensors that capture practical environmental metrics, recording temperature variations, tracking physical motion, or measuring fluid dynamics. This layer also includes actuators. While sensors read data, actuators receive digital commands and execute physical actions, like triggering a mechanical valve or sounding an alarm. But capturing reality is only half the problem. A sensor logging 1,000 data points a second is useless if it has no way to transmit that volume of information up the chain. That data must pass through the middle tier, the network layer. This schematic shows IoT gateways serving as aggregators. They collect localized sensor readings from the perception layer before pushing them toward wider networks. Here, the engineering topology shifts away from specialized hardware and bridges into standard IT protocols like local and wide area networks. Engineers must deploy diverse wireless connectivity standards at this stage, ranging from low-energy Bluetooth to high-bandwidth LTE, to balance geographic distances and strict power constraints. Because all data funnels through this tier, the network layer is the architectural bottleneck. It dictates the speed, reliability, and security of the entire physical-to-digital transition. Once the data clears the network, it reaches the apex of the architecture, the application layer. This layer relies on massive cloud infrastructure. It houses centralized processing power and storage capabilities far beyond what edge devices can handle. This completes the core operational loop. First, edge sensors push raw data up through the network to these centralized servers. Next, the central system actively ingests and queries this continuous incoming stream. Finally, the system analyzes the data against programmed models. It can visualize long-term trends for human users or send commands back down the chain to trigger automated responses in the physical actuators. The application layer generates business intelligence. Here, the system synthesizes raw, disparate data into insights used to guide organizational decisions. This architectural blueprint is independent of the specific industrial application. It is used across the global economy. This grid maps diverse IoT applications. In heavy industry, the exact same data flow powers structural asset monitoring, tracking stress tolerances on a crane in real time. In public utilities, smart grids balance municipal load distribution based on constant feedback from edge sensors in individual homes. This chart details the global trends of IoT implementation. We see the same underlying structure dictating smart city parking management, agricultural climate tracking, and global fleet logistics. Whether an engineer is designing a localized home automation system or a citywide power grid, they are relying on the exact same three-layer stack. As IoT networks expand from dozens of devices to thousands of nodes, the relationship between operational efficiency and system risk begins to shift. This graphic breaks down the benefits generated by the application layer. Organizations see immense increases in efficiency, productivity, and profitability. By establishing continuous, real-time data collection, a business shifts from reactive management to proactive optimization. However, As these deployments grow, the same architecture that enables high-level optimization begins to expose critical points of failure. Deploying thousands of nodes introduces compounding systemic vulnerabilities. Engineers face immediate operational drawbacks. There is a severe lack of industry standardization, resulting in widespread compatibility issues between hardware manufactured by different vendors. Logistically, deploying highly calibrated edge sensors carries high production costs, and the resulting data lakes quickly overwhelm inadequate storage capacities. Beyond hardware logistics, the most critical threats are cybersecurity and data privacy. The perception layer expands a network's attack surface. Every individual sensor or actuator is a potential backdoor into the system. Take common consumer-grade IP cameras. Their embedded microcontrollers often lack rigorous security protocols. An exploit in just one of these edge devices can allow a bad actor to bypass the network layer entirely, gaining direct access to corrupt centralized software and data. This generates severe privacy concerns. Local monitors operating in homes, businesses, and public spaces are constantly feeding sensitive behavioral data to centralized servers. Modern IoT engineering requires securing, standardizing, and scaling the three-layer architecture against these inevitable systemic threats.